module. You will learn about redox reactions and electrode processes. Let's revisit a redox reaction that we've seen. Here, we place a zinc rod in copper nitrate solution. After a while, the color of the solution becomes pale blue, and finally, it becomes colorless. The zinc rod, on the other hand, gets coated with reddish metallic copper. In this reaction, zinc is oxidized to zinc ions and copper 2 plus ions are reduced to form copper. This reaction took place in an open vessel, and the chemical energy from the reaction was released as heat. Think about it. Is it possible to convert the chemical energy into electrical energy? Yes, it is. Let's see how. We place the zinc rod in 1 molar zinc sulfate solution. Then, we place the copper rod in 1 molar copper sulfate solution. In each beaker, the reaction takes place at the interface between the metal and its salt solution, and both the oxidized and reduced forms of the same species are present. This is also known as a redox couple. A redox couple is defined as a combination of the oxidized and reduced forms of the same substance taking part in a redox reaction. Now, we connect the two solutions by using a salt bridge. A salt bridge is a U-tube filled with potassium chloride or ammonium nitrate, usually solidified by boiling with agar and later cooling to a jelly-like substance. It is an inert electrolyte and is a substance whose ions neither take part in a redox reaction nor do react with the solutions in the two beakers. Next, we connect the two ends of a voltmeter to zinc and copper electrodes by means of wires. When the switch is in the off position, no reaction takes place and current does not flow. As soon as the switch is in the on position, current flows and the reading in the voltmeter changes, indicating that current is passing through it. The current is caused due to the chemical reaction taking place between the two beakers. Since zinc is a more active metal than copper, it loses electrons and gets oxidized. The equation for this reaction can be expressed as zinc atom loses 2 electrons to form zinc ions. The electrons move through the voltmeter wire and reach the copper rod. When the electrons lost by zinc reach the copper rod, they combine with the copper 2 plus ions to form neutral copper atoms, which get deposited on the copper rod. The equation for this reaction can be expressed as copper 2 plus ions gain 2 electrons and form copper metal. As the reaction continues, the excess zinc ions accumulate around the zinc rod in the zinc solution. Due to this, any further oxidation of zinc stops as the repulsion among Zn2 plus ions increases. Similarly, copper 2 plus ions reduce to copper atoms and deposit on the copper rod. This loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions in the solution. This prevents the further reduction of copper ions. As a result, the overall reaction stops and also the current in the setup stops. To avoid such a situation, the salt bridge plays an active role. The positive potassium ions move from the salt bridge into the copper solution, thereby neutralizing the negative charge. On the other hand, the negative chloride ions move from the salt bridge into the zinc solution and neutralize the positive charge. Thus, reaction goes on continuously till the solutions get exhausted. The reaction stops when either the zinc rod or the copper ions are depleted. The overall equation for the reaction is copper 2 ions react with zinc metal to form zinc 2 plus ions and copper. Note that Zn loses electrons and undergoes oxidation, and hence the beaker in which zinc rod is immersed in zinc sulfate solution is called oxidation half cell. The electrode at which oxidation takes place is called anode. On the other hand, the beaker in which copper rod is dipped in copper sulfate solution, reduction of copper ions is taking place and is referred to as reduction half cell. The electrode at which reduction takes place is called cathode. During the cell notation, a slash is used to separate the oxidized form and the reduced form in a couple. The overall cell is represented by writing oxidation half cell on the left-hand side and reduction half cell on the right-hand side, both separated by two vertical lines. Electrons produced at anode due to oxidation of zinc travel through the external circuit to cathode, where they reduce copper ions. Note that the current flow is in the opposite direction to the electron flow. In this experiment, the two redox couples are zinc and zinc 2 plus ions and copper 2 plus ions and copper. The apparatus set up for this experiment is known as the galvanic cell. The galvanic cell was invented by an Italian anatomist, Luigi Galvani. Note that there are many factors that determine the amount of electric current produced by a galvanic cell. The most important factor is the tendency of a metal to lose electrons. Between the two electrodes, one has a tendency to lose electrons, while the other has a tendency to gain electrons. The potential of any electrode, commonly known as electrode potential, is the potential difference between it and the electrolyte surrounding the electrode. The electrode potential of an electrode depends on the nature of the metal, concentration of the ions, and the temperature of an electrolyte. If the concentration of each species taking part in the electrode reaction is taken as unity and temperature is taken as 298 Kelvin, then the potential of each electrode is known as the standard electrode potential and is represented as E0. By convention, the standard electrode potential of hydrogen electrode is taken as 0. Chemists have created a table that lists the tendency of various substances to lose electrons in a galvanic cell. Note that The values of standard electrode potentials are relative to the standard hydrogen electrode. A metal with a higher standard reduction potential can be easily reduced, and hence is a better oxidizing agent. For example, fluorine has a standard electrode potential of plus 2.87 volts, while lithium has a standard potential of minus 3.05 volts. Thus, fluorine reduces easily and is the strongest oxidizing agent. On the other hand, lithium undergoes oxidation as is the strongest reducing agent. You have now reached the end of this module. In this module, you have learned that redox reactions in which the oxidation and reduction reactions occur in the same vessel are called direct redox reactions. A redox couple is defined as a combination of the oxidized and reduced forms of the same substance taking part in an oxidation or reduction half reaction. The tendency of a substance to lose or gain electrodes in galvanic cell is known as the electrode potential. The electrode potential of an electrode depends on the concentration of ions and the temperature of the solution the electrode is in.